Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 3, writing products as sums and writing sums as products. Kind of the distributive property or factoring, and we'll get into more detail about that in a moment. So let's start with a classwork opening exercise, and it says solve the problem using a tape diagram. A sum of money was shared between George and Benjamin. So I just started this one when I was waiting for this to buffer. And so here we go. Benjamin. Okay. So let me see if I can just clean this up so you can read it. Okay, that's better. Okay, so now if I'm going to do a if I'm going to make a tape diagram for George, and their ratio is 3 to 4, that means George gets 3 squares. So there's 1. There's 2. And there's 3 equal squares. So Benjamin, it's the ratio of 3 to 4. So I'm going to do the same here for Benjamin. And 1 more. So there's 4. Okay, if the sum of money was $56, that means all of these represent $56. And I want to know how much George gets. So this is the answering the question is knowing how much George gets. So if I divide $56 evenly between 7 squares, that's the same as just divide by 7, and I get 8. Okay? So if this is 8, they're all 8. 7 times 8 is $56. George has 3 bundles of 8, which is a total of $24. That is the answer to the question. How much did George get? Example 1. Represent 3 plus 2 using a tape. Okay? Well, if I did a tape diagram, and this was 3, there's 3. And then if I add 2 to it, I'll just change color so you know that it's the 2. Then I add 2 more to it. Then my tape diagram is going to look like this. Okay? It's going to extend out. And we're going to have 5 total squares. 3 plus 2 is a total of 5. So this represents our 3. This represents our 2. Okay? Represent x plus 2 using a tape diagram. Well, in this case, we want to just make sure x doesn't look the same as a constant. So there's my x, and then if I throw 2 more squares onto that, look like this. Okay, so there's x, and there's my 2. Okay, so this is it. Now it says to draw a rectangular array for 3 times 3 plus 2. Well, if I do the 3 plus 2 again, it's the same diagram from the first page. There's my 3. Okay, and then here is my 2. I'll use a different color. Okay, so there's 1 3 plus 2, but we need 3 of them. So I'm just going to repeat that 2 more times. Okay. Okay. So this is 3. This is 2. And that's these inside here. And then the outside number, this 3, will be represented as the height, 3. So if I have 3 times 3, there's 9 squares. Now if I have 3 times 2, there's 6 squares. And the total of 9 plus 6 is 15. And if I add 3 plus 2 and get 5, 5 times 3 is also 15. Okay, so now let's draw an array for 3 times x plus 2. So it's going to look like this. It's going to be 3 of them. Okay, but I want an x. And I want plus 2. Okay, and I want 3 of those. So I'm going to continue this down. So there's my 3 groups of 2. Right? So this is x. This is 2. And this is my height, 3. So I have 3 of them. So I have 3x if I multiply plus 6. We'll get to that. So this is the key term down below here, distributive property. The distributive property can be written as the identity A times the quantity B plus C equals AB plus AC for all numbers A, B, and C. So it's true for any number you substitute in. So exercise 1 says determine the area of each region using the distributive property. Okay. So what we're really doing here is let me get my ruler and I'll explain this better. Okay, so I'll bring my ruler down. So I'm not going to do this whole thing, but if I drew a straight line there, okay, and I move my ruler, and rotate it, vertical, and move it over here. Then if I draw a line, this, okay, so what I'm doing is I'm making tiny little squares. So if I continue this, what I would be doing is making each square equivalent, and there'd be 16 of them going across the top here, and then be 5 more in here. It would take way too long for me to fill in, so I'm not going to do it. And then there'd be 11 rows going down this way. So then it'd be asking how many little squares are there in each section. So again, I'd be continuing all of these all the way across to here, and then also doing these like this. Okay, so that was messy. So anyway, we would continue doing that. So what we're really going to do is find out if I have 11 here and 11 here, and I have, or I'm sorry, 16 here, 16 here, and 11 rows of 16. That is the same as saying 11 times 16, which is 176. Okay. And if I take 11 times 5, that's 55. So it says determine the area of each region using the distributive property. I found the area of each region. This region here is 176, and this region here is 50. Okay. All right, example 2. Draw a tape diagram to represent each expression. Okay, so I have x plus 1. So if I make x1 rectangle, and I make another one, y, make it larger, so they're not equal, there's x plus 1. So I call this x, call this y. What I need to do that repeatedly, the number of times I have it. So it's plus x plus y, and then plus x plus 1. Okay, so I have x plus y, x plus y, x plus y. Here's my x, here's my y, here's my x, here's my... B says to draw the tape diagram of this expression, x plus x plus x, and then y plus y plus y. So it's going to be this rectangle here 3 times by itself. In other words, no y's. Repeated 3 times, so I'm going to put this one here now. Okay, and then put this one here. So there's x plus x plus x, and then y is a little longer. There's 3 of those. So there's y plus y plus y. Okay, if I continue down here to 3x times 3y plus 3y, then I would just simply move these. Here, let me Just a moment. Okay, so if I have 3x plus 3y, then it's basically the same thing. So I'm going to take this, there's my 3x, there's my 3y, but I'm just going to connect these. So there's 3x plus 3. Okay. And then finally 3 times the quantity x plus y. This one's a little bit different. So this one I can just make one rectangle instead of breaking it all up into pieces and call that x, and then make another rectangle different sized, make the y larger. There's y, so there's x, there's y, and the number out in front is your height, so we're doing area. So 3 times x is 3x, 3 times y is 3y. So that would be the quantity 3x plus 3y. Okay. Example 3. Find an equivalent expression by modeling with a rectangular array and applying the distributive property to the expression 5 times the quantity 8x plus 3. So what they want us to do is make an array. So I will draw one large rectangle that will represent 8x. So I'll call this a length of 8x. And then I'm going to put another piece on it. I'm going to call that piece 3. So we can also break it up and say 3 vertical. And then it is going to be a height of 5. Okay, so when I take 5 times 8x, I get 40x. 5 times 3, 15. The two pieces in between tell us to multiply or add. So in order to do this problem, it says apply the distributive property. So there's my rectangular array. Now to apply the distributive property, I take the original problem, 5 times the quantity 8x plus 3, and I would distribute. So 5 times 8 is 40x. 5 times positive 3 is a positive 15. Okay? And then it says, we should always check our answer, see if it's true. So our original problem is 5 times the quantity 8x plus 3. And we just said it was equal to 40x plus 15. Well, the easiest way to tell if something is true or not is to substitute in a value other than any identity, so don't use 0 or 1. So we can plug in, let x equal 2. So over here I'll just write that. Let x equal 2. Alright, so I'm going to rewrite this. 5 times 8, let x equal 2. There's an x, so I'm going to replace that with a 2, which means to multiply by 2, plus 3 equals 40. There's another x, x is 2, so I'm going to replace x with 2, okay. And then I'm going to add 15. And PEMDAS says to do inside operations first, the parentheses with a grouping, and within that we have multiplication and addition. So I'm just going to show all of my steps, and multiply before you add gives me that, and then 40 times 2 is 80 plus 15. Okay, now the grouping inside, I would leave the 5 there again. 16 plus 3 is 19, and then 80 plus 15 is 95. And if I multiply 9 times 5, I get 45, carry the 4. 5 times 1 is 5, plus 4 is 9. And sure enough, I got 95 equals 95. So this is equivalent to 40. Exercise 2, for parts A and B, draw an array for each expression and apply the distributive property. Substitute the given number in and find its equivalence. So there's 3 things we have to do. First thing is draw an array. So here is x, here is 1, here is 2. Okay, here's my array. 2 times x is 2x, 2 times 1 is 2, so I get 2x plus 2. if I do it with the distributive property, okay, actually let's show it first. 2 times x, 2x. 2 times 1 plus 2. Okay? So I have 2 parentheses x plus 1 equals 2x plus 2. And we want to check it when x equals 5. Okay, so I'm going to rewrite that. 2 parentheses 5 plus 1 equals 2 times 5 plus 2. Okay? PEMDAS says to do the grouping first. 5 times 2 is 10. 6 times 2 is 12. 10 plus 2 is 12. And they check. They are equal. Okay? Next problem. 10 times 2c plus 5. So before I get ahead of myself here, I have to do what they asked for, draw an array. So I'm going to draw a rectangle, and I'm going to call it 2c. That was my first term. Then I'm going to draw another rectangle that's smaller. That's going to be my constant. I'm going to call that 5. The height is what is outside, so that's 10. 10 times 2c, 20c. 10 times 5, 50. Okay, so then if I take 10 times 2c plus 5 and distribute, 10 times 2c equals 20c, and 10 times 5 is 50. So I got the same answer as this here. Now it says to let c equal 1. So now I'm going to redo this problem. 10 times 2 times 1 plus 5 equals 20 times 1 my c plus 50. Okay. PEMDAS says to multiply first, so we have 10 times 2 times 1, which is 2, plus 5. 10 times 2 plus 5, which is 7. And 10 times 7 is 70. If I come over to the other side, I get 20 times 1 is 20, plus 50, and that also equals 70. Okay, just took one less step there, but 70 equals 70. Okay. Alright, for this one, for part C and D, apply the distributive property, substitute, and demonstrate equivalency. So now we're not doing the arrays anymore. So 3 times 4f is 12f. 3 times a negative 1 is negative 3. And then we're going to substitute in our f, which is 2. 12 times 2 is 24, minus 3. The answer is 22. Okay? It says to demonstrate equivalency. Okay? So now I've got to take the original and make sure it's equal to 12f minus 3 by plugging into here. So I've already done it over here, so let me just save some time and erase that just simply with this all over here. Okay. So I've already done the right side. So I did 3 times 4f equals 12f, 3 times negative 1 is negative 3. Now I just need to prove that if I plug in 2 on this, 3 times 4 times 2 minus 1 equals, and then do PEMDAS. 4 times 2 is 8 minus 1. 8 minus 1 is 7. 3 times 7 is 21. So I got the same answer. Okay? So this one here, I'm just going to write 9, negative 3r minus 11. I just rewrote it. I'm going to distribute. Positive times a negative equals a negative. 9 times 3, 27. put the variable after. Okay. 9 positive times a negative, negative 9 times 11, 90. So I want to prove that this is equal to that when R is 10. Okay. So now I'm going to rewrite this. 9 times negative 3, place R with 10, minus 11, equals negative 27, place R with 10, minus 90. Okay, this is going to say 9. Negative 3 times 10 is negative 30, minus 11, equals 27 times 10 is 270, minus 90, 9. And negative 30 minus 11 is negative 41. And negative 270 minus 100 is negative 370. But I'm taking away only 99, so it's going to be negative 369. 9 times 1 is 9. 9 times 4 is 36. Positive times negative is negative. And they are equivalent. Example 4. Rewrite the expression 6x plus 15 divided by 3 in standard form using the distributive form. So what that means is we're going to take 6x plus 15 quantity divided by 3. We're still going to use the distributive property. We're going to distribute the 3 to both parts. So I'm going to rewrite this as 6x over 3, 6x divided by 3, plus 15 divided by 3. 6 divided by 3 is 2. 15 divided by 3 is 4. Okay. So this one just said to rewrite it in standard form. Standard form is when I have a coefficient and a variable first, and the constant comes second, no like terms. Exercise 3. Rewrite the expression in standard form. Same thing. So it's going to be 2b, we're going to distribute, divided by 2, plus 12 divided by 2. 2 divided by 2 is 1, so I'm just left with b, plus 12 divided by 2 is 6. B is a variable all by itself. This is b. Why they would choose a ground with a b and a 6, but anyway, b and a 6. Alright, again, distribute, 20r divided by 4, what's your sign? Minus 8. 20 divided by 4 is 5, keep the r, 8 divided by 4 is 2, keep the sign. Nothing can be reduced or defined, 5r minus 2. 49 divided by 7 and 7 divided by 7. So it's 49 g divided by 7 minus 7 divided by 7. 49 divided by 7 is 7. Bring down your g. 7 minus 7 is 1. 7g minus 1. Okay. Now we're going the other way. We're going to expand. We have 3 term polynomial, that's called a trinomial, times the constant, which will become the coefficient of each term. So 4 times x is 4x, 4 times y is 4y, plus 4 times z, 4z. Okay. Exercise 4. Expand the expression from a product to a sum by removing grouping symbols using an area model and the repeated use of the distributive property. Okay, so there's a couple things we have to do in this one. We want to do an area model and repeated use of the distributive property. So if I take the original problem right here, and I'll show all my work this time. 3 times x is just, I'm going to represent it as 3 times x plus 3 times 2y plus 3 times 5z. Okay, that's going to give me 3x, plus 3 times 2y is 6y, plus 3 times 5 is 15. Okay. Now if I were to do this as an array, or an area model, array, then I would have a rectangle to represent length x, a different sized rectangle to represent y, and different sized rectangle to represent z. And actually this isn't just y, this is 2y, and this is 5z. Okay, so that's the length 5z, that's the length 2y, that's the length x. My height is the number outside, which is 3. 3 area is length times width, so 3 times x is 3x, 3 times 2y is 6y, and 3 times 5z is 15. Example 6. A square fountain area with the side length s feet is bordered by a single row of square tiles as shown. Express the total number of tiles needed in terms of s 3 different ways. Okay, so this is s, so I'm just going to use this as a template, if you will. I'm going to cut that out, and then I'm going to move it. So that's going to go there. So there's my tile size. So that's 1. Right? So if I call that length 1, and that's length 1. It's 1 foot by 1 foot. Okay, if I continue doing that, I do another one, and then move it over. I'll put this one here. Again, length 1 by. Okay, I need to do this for every corner. There. That's 1. That's 1. And the last one. So what I'm really accounting for here is the area that's taken up by corners. That's not represented by the painting or whatever's inside. Okay, so there, I've done the corners. So what I'm trying to say is, this is a length of s. So if you represent that as an array, that's s. This is length s. So on, all the way around. These pieces are length s, because this is a square inside that is s feet long by s feet. So if I split this up like this, then this is length s, and this is length 1. So how do I represent this side here? Well, I have this s plus 1 plus 1. So that'd be s plus 2. So if I do the same over here, I'm going to get s plus 1 plus 1, which is s plus 2. Be careful, I cannot do that down here. I've already accounted for this square here when I counted this side and this side. Now the only thing that's left is this black rectangle in here that's represented by s. So this is s, this is s. Do not count those squares more than once. We have 1, 2, 3, 4 green squares. Here's representing 2, here's representing 2. That's 4. Stop, do not count for more than one. They are there. So this is left. This is right. This is top. This is bottom. So if I express the total number of tiles needed, then it would be s plus 2 plus s plus 2 plus s plus s. Okay. And I can rearrange those and just say it's 1, 2, 3, 4 s's plus 2, which is 4. Okay? So I can represent it as 4s plus 4. I could factor out this 4 now. Backward distribute in the opposite direction is called factor. 4s divided by 4 is s. 4 divided by 4 is 1. So this is a solution. This is a solution. That's 2. They said 3 different. Okay. One other way is I could take the s plus 2's, and I'll do it over here. There's 2 of them. Like this, s plus 2 is here, and s plus 2 is here. 2 s plus 2's plus 2s. Okay, that's different than these two. Right? And then we can actually simplify this and say that is 2s plus 4. Our distribution plus 2s. Combining like terms, we get 4s plus 4, and sure enough, that's equal to that. Okay? So here is our other solution. So there's many different ways we can do this. Okay. That's the end of lesson 3. Go do your problems.